Start this. We're good. I'm not on mute now. I'm terrified for every class, even not this class. I'm like, I want to be on mute again. Okay. Looks like we're all good. I heard that Jenna was on her best behavior. You saw her on Friday. She said you guys were great and that you got through 2.3 and 2.4. So I'm just going to take her word for it, which we were talking about earlier. Feels kind of weird for me, but anyways, we'll go into 2.5. So today we're going to do 2.5 and 2.6, and then 2.7 and 2.8 next day. And then the following week, right, you've got your first test, which is going to be on chapters 1 and 2. So test number 1 is on Tuesday. Only because I thought it was a little bit mean to put it on the Friday before reading break, especially when our class is from 11 to 1. So I put it on the Tuesday, and then you can do whatever you want for reading break. Wink, wink. So test number 1 is on Tuesday, and I can't remember what date that is. February 11th, thank you. And it's on chapters 1 through 2. I guess 1 and 2 would have sufficed. Jen and I are working on a practice test so that you'll have a practice test. But like I said, we will be pulling questions for the actual test from the problems that we've given you in the notes, right? And so I mean, if you've done all of those, and that's a lot, then you'll be more than ready for the test, right? But even with the practice test, what you'll see is it'll just be the specific sections that we want you to focus on, right? And so, so you should feel prepared for the test. And like I said, because I didn't want to have it the Friday before reading break, we're not going to be able to do a review class, but you'll have the practice test, you'll have the solutions to the practice test, right? And you can ask me questions and stuff about it. We're working on it right now. I think Jenna was going to send me something maybe today, hopefully. But I definitely want to give it to you on Friday when we meet, but hopefully before then. Yeah, definitely sooner rather than later. I know. Okay. Yeah, any questions about the test a week from now? Ooh. Okay. And so what we're kind of tag teaming it. So what I did is I went through the final and I pulled the questions that you need for the final. So I definitely want to have those on test 1. And then there's a couple of other things that we want to test on test 1 as well. And so that'll be just what you should expect, right? But always preparing you for the final exam. I was looking at the schedule, and on the Friday before reading break, we're only supposed to cover 1 section. And I think because of that move, right? And so I want to ask you guys, do you want to have class or do you want to not have a class? Because we could easily, because then we're supposed to cover 3.1 again on the Tuesday after reading break. So we really don't miss any time. I think it was just me not wanting to have the test on the Friday.
I'm not going to be here Friday anyway, so I would prefer it.
So how about no class on Friday the 14th? Good? Everyone's okay with that? If you're mad about it, You don't have to tell me now, but you should tell me later. But hopefully no one's mad about it. Okay. Good. But if you are, you have to tell me later. So then you heard it here first. No class on Friday, February 14th. That's the day before reading break. And I guess also Valentine's Day, but that's actually not why. Phew. Great. That's perfect. Let's say that then. If you know anyone who's not here today and you run into them, maybe let them know. They're probably going to skip it anyways, since they're not here today. So I'm not too worried, but I'll post something on Moodle as well and just kind of make sure that you know. Okay, so that's what I've got going on. The chapter 2 quizzes, I made them due before the test because I want you to have done them to practice for the test, right? And so that's the only reason that the due date is a little bit shorter. And so the chapter 2 quizzes are due, and does anyone know? I think I made them due the 11th. The 11th are due on Tuesday, February 11th at midnight as per usual, but do them before the test for practice. I'll say for extra practice. So you have more practice. Okay. Good. That was all the housekeeping things I think that I wanted to do. How about we talk about section 2.5, or are there any questions before we do? So 2.5 is on linear functions. Linear functions, so we've talked about linear equations, right? Straight lines. Now we've graduated to talking about functions, right? There's really no difference between equations and functions. It's just that it takes an input of x and it spits out a value of y. So a linear function is just a straight line function. And so we've got the little definition here. Copy. Here, so this equation or this definition should not feel that foreign, right? Because what we've seen before are things like y equals mx plus b. We know how that behaves, right? And so that's just a straight line equation. Now we've got a straight line function or a linear function, and whatever's attached to the x is the slope, and whatever's on its own is the y-intercept. Right? And so what we can do, right, is usually we want to draw these straight lines, right? There's not much else that we can do, right? And so to draw a straight line, or to, I shouldn't say draw, maybe I should say graph. To graph, no one likes graphing, right? But we are graphing if we're drawing. So to graph a linear function, all we need are 2 points on the line, right? And they can be any 2 points, right? And so what we do is we just pick a value of x, figure out what the value of y is, and then pick another value of x, figure out what the other value of y is, And then we can connect those dots and extend the line, right? We already talked about drawing straight lines, and we'll do a little bit more today. So to graph a linear function, we need to find at least 2 points on the line. Right. Then we can connect them and extend the line. Then we use a straight edge. Right? And anything that you have handy, right? The edge of your calculator, you can use to connect your dots. I've seen a lot of credit cards being used, right? That's a nice straight edge. Connect the dots. Yep, that's nice. Often, if I'm in a pinch, I'll just kind of gently fold over the page and use that as my straight edge, right? So you've got a ton of straight edges. Does not have to be a ruler. Right, so then we use a straight edge to connect the dots. Then we extend the line. Oops. And so we've got a couple of examples here. First of all, let's just have a look at that first section of questions. It's just identifying linear functions, which is going to be more useful than you might imagine, right? Because what's going to be helpful is if you're able to recognize that you could reorganize something into a straight line, right? That's going to be really helpful. And so just looking at these, well, a straight line, right, has the form ax plus b or mx plus b, right? Meaning there's one x and potentially one other just constant, right? And so we're looking for one x, right, with a power of 1 and a constant, and that constant can be 0, right? And so if you're able to quickly rearrange things into ax plus b or mx plus b, right, then you've got a straight line. And it's easy to think about how that behaves. And so we like to go for the last one, but also I want to look at 13 and 14. So 13 says f of x is x plus 1 squared. I already know that I'm going to get an x squared term in here, right? So it's not going to be a linear equation anymore, or a linear function, right? But this becomes x plus 1 times x plus 1, which is x squared plus 2x plus 1. This is not a linear function. Hmm. 14, though, says f of x is 1/2 3x minus 1. Even if I expand this, right, I get 3 over 2x minus 1/2. This is a linear function. is a linear function with slope equal to 3 over 2, right? Because that's what's attached to the x after I've simplified everything, and y-intercept equal to -1/2, because that's the constant in there. 10? Yeah. Sure. 10 root x plus 1. So 10 says f of x is a root x plus 1. Yeah. So this one, nice catch. A little bit trickier, right? The slope would be 1, except we need a power of 1 for the x, right? And the root of x we can actually rewrite as x is 1/2 and then plus 1, right? So it's not a linear function. Good. Not a linear function. Because we have to have a power of 1 for the x. That's right. Yeah, so just kind of glancing at these, 7 looks good, right? 8 looks good. 9, that looks bad, right? Because you get an x to the power of 2. 10 we just did. 11 looks fine, right? Because you can split that 5 and have x over 5 plus 1 over 5, right? So that one's fine. Same thing with 12. You can get 2x over x, which is just going to be 2, right? And then minus 3 over x. Nope. Because the x is in the denominator. Yeah, no go. Yeah.
11, can you multiply the 5 onto the top? Or
no, you would have to, you could multiply by 5 over 5, but it's not going to do anything, right? So then you would just get 5 over 25. Yeah, so it wouldn't help. Yeah, sorry, I jumped the gun on 12 because then you've got 3 over x. X is in the denominator, and that's not a linear function. And then we talked about 13 and we did 14. Nice. How about we do, so for 15 and 18, where we're graphing linear functions, right? I don't have any grid paper or anything, so we're just going to sketch out the axes approximately. If you have to draw a straight line on the test, right, I would give you axes and you would have them. Now we'll do the added work of sketching them out. For the given linear function, make a table of values and sketch its graph. What's the slope of the graph? So when it says table of values, what it's actually saying is find 2 points on the line. Usually how we do that is we organize our work as x and f of x, right? This would be a table of values. And so I'm saying I'm going to pick a value of x and then another value of x, right? And so I'm just going to denote that as x1, x2. And then I'm going to find f of x1 and f of x2, whatever those 2 points are. Because I only need 2 points.
we don't know the value of x. So then
That's right. Yeah, so you can just pick any 2 values of x. But if I've given you a graph, you'll want to pick values of x that are on the graph, right? Because later what we're going to do is this is point 1. Oops, point number 1, and this is point number 2. Let's do one so we see what's going on here. Should we do, let's do 16 and then 18. How about that? Because 16 is a little bit easier. So if we're doing 16, then we've got g of x is 4 minus 2x. So if I ask you to draw this line, right, we know that, okay, first I have to find 2 points, right? How I'm going to organize that work, and I'm going to scoot this so it's all on the same page here. How I'm going to organize this is I'm going to say x is going to give some g of x. And g of x we know is equal to 4 minus 2x. I can pick any value of x, right? Because any value of x is going to be on this line. And so I like to pick convenient values of x, right? And so 0 is usually a go-to, right? So if I let x be 0, I can find g of 0 is 4 minus 2 times 0, which is 4. Which says that the point that I just found is at 0, 4. Another convenient value of x, well, if you look at it, 2 might be convenient because we get to 0, right? But even if you don't see that, if you use something like 1 where it's easy to calculate, then let's use 1. Then we get 4 minus 2 times 1 is at 2. So the point that I just found here is at 1, 2. Remember, the points are always at x comma y in round brackets. And here, I'll just make a note that you can pick any values of x, right? So, bless you, pick any value of x. Oops, bless you. So now, if I have to plot 0, 4, and 1, 2, well, I have to make sure that I have room on my x-axis for a 0 and a 1, and then on my y-axis at least for 2 and 4, right? And so I'll just kind of sketch something out here. 1, 2, 3, 4. 1, 2, 3, 4. 0, 4. Keeping in mind that here at the y-axis, oops, I'm at x equals 0. So now if I'm plotting 0, 4, I'm up here, 0, x is 0, y is 4. And what we want to do is we want to label this thing 0, 4. And then I'm at y, 1, 2, so 1, x is 1, y is 2. There. Now I've got 2 points on the graph, and now I'm going to connect these two with a straight edge. Let's see if I can do it. I should actually extend the line probably a little bit more. Of course, my axes aren't that good, right? But if we have a look at 4 minus 2x, we've got a slope of -2, which you can confirm with the rise over run, right? And you've got a y-intercept of +4. And so it looks like what we're expecting it to look like, and that's always good. Nice. So the key is just find 2 points on this line, plot them, connect the line, and you're done. How about we do something a little bit more complicated? Let's have a look at that 18. H of t is 1/2 minus 3 over 4t. Okay. (18) says h of t is 1/2 minus 3 over 4t. So again, now my variable is t, but nothing really changes, right? T is my x essentially. And so I have to find about 2 values of t and find the output h of t. And I like to have a reminder of what h of t is. It's 1/2 minus 3 over 4t. Now, just because I don't want to have to deal with fractions, I'm going to pick convenient values of t, right, that make me not have to deal with fractions. And so or at least as many fractions, right? And so at least if I pick a multiple of 4, right, then that's going to cancel in the bottom. And even maybe t equals 0 is still pretty good, right? Leaves me at 1/2. So usually plugging in 0 is a pretty good way to go. So let's use that. So 0, I'm at 1/2 minus 3 over 4 times 0, which is 1/2. So then I'll make a note here. I'm at 0, 1/2. Oops. How about we pick 4 now, right? Just to cancel that 4 in the denominator. So if I let t be 4, I get 1/2 minus 3 over 4 times 4. Puts me at 1/2 minus 3. And whether you want to find a common denominator, right? Or if you just want to say, well, I'm pretty sure that's -2.5, right? That works too. And because we're working on the scale here, on a number scale, right? Maybe a decimal is easier to think about than a fraction anyways, right? So you could just use your calculator too. So now I'm at 4, -2.5. So now I can plot these. Because we're sketching out our axes, right? I need to make sure that for my x's, I have room for 0 to 4. And on my y's, I have room from 1/2 to -2.5. And so now I know that my axes are going to have to go down on the lower end. So here I'm at -1, -2. Here I'm at 1, 2, 3, 4. My first point, 0, 1/2, let's say puts me here. 0, 1/2. If I'm at 4, -2.5, I'll be somewhere down here. So again, we can just connect these two and extend the line. Oh, did a bad job there. I went under and over for some. There. close enough. So the table of values is just organizing our work for finding these 2 points. Any questions about that one? Okay. Then let's talk about the, oops, 2.6, no, here. The slope and the rate of change. We'll just establish that they're the same thing. And so I drew my line too far here. There. Okay. So the slope of a line, right? We can also think of it as the rate of change, right? How fast is this thing changing over X? Right? And this is something that comes back to haunt you for all of calculus, right? Because we're going to talk about the slope of a line, and then, but we're also going to call it the rate of change, right? So for us, we just need to get used to the fact that they're the same, right? And so the slope, if you know the slope, then you know the rate of change, right? And so here, slope is the rate of change, basically. So question 19 and 26, or through 26, oops, ta-da, asks you to sketch the graph, which we already did too, so I'll leave that to you guys. And then you want to find the slope of the graph, which you can actually just do from the equation, right? And then find the rate of change of the function. Well, they're going to be the same, right? And so the slope and the rate of change will always be the same. So looking at 26, even if we don't graph it, we can say, well, g of x is 5 over 4x minus 10. And so the slope is 5 over 4, which is also the rate of change. So not too bad. I threw in an example, or a couple more examples of just linear functions given verbally, but also if I give you a table of points that are on this line. Let's see here. If we look at 30, for example, if we get a verbal description, and luckily you have it in front of you, it's really small up there, the graph of the linear function k has a slope of -4 over 5 and y-intercept -2. And so we're supposed to express the function. In this case, it's a linear function called k. And so k of x is going to be the slope -4 over 5x minus 2, right? Because it has a y-intercept of -2. in 31 and 32, well, the rate of change, right, is the slope. So the slope is -12, and then the initial value is 100, which means y-intercept equals 100. And so what we get here for 28 is the function is called g, and let's use x. It has a slope of -12 times x plus 100, the y-intercept. Is that good? So here we have a table of values. So before we were finding a table of values, but we also know that we only need 2 points on the line, right, in order to find this line. And so if we have a table of values of more than 2 points, then that's fine, but they're all going to be on the straight line anyways. And so we're going to find the rate of change of f and then rewrite f of x as a linear function. So if we have a look at 32, we need to find the slope, right? One thing we could do is we could plot all these points and connect the line, find the rise over run. Or what we could do is we could just say that the slope, m, is f of x2 minus f of x1 over x2 minus x1. And then I can just pick any one of these values to be my x1 and x2. And so if I let x1 be, let's use the first one, -3, even though it might be easier to use positive values, but I'll use -3. And f of x1, we're told, is 11. Right? The y at -3 is 11. And let x2 be 0. And f of x2 is 2. Okay. So now I can find my slope, which is also my rate of change. So f of x2 minus f of x1, because I want to find the rise, might be negative, but that's okay, over x2 minus x1 is 11 minus 2 over -3 minus 0. That puts me at, hopefully, 9. 11 minus 2 is 9 over -3. I get a slope of -3. So that's my slope. My rate of change is also -3, right? So I've got this downward sloping line. Right? We also wanted to write it in the form f of x is ax plus b, which means we have to find the y-intercept. Luckily, we know that when x is 0, y is 2. Right? And so here, just make a note that this here is the y-intercept. So therefore, f of x is ax plus b, right? Or mx plus b maybe. Doesn't actually matter. -3x plus, what did we say it was? 2. That might very well have happened. I sure did. Makes a difference too, doesn't it? Rats. Thank you, thank you. 0 minus -3. Oh, I messed it up all around. I bungled it.
But doesn't that not matter which?
It doesn't, but I should probably, yeah, as long as you're consistent, yeah, exactly. But I should probably do it properly. 2 minus 11. There. So as long as you're consistent, you will end up at the same thing. But like I said, because I had let those two be those two things, I should probably plug them in properly. Ah. How's that looking? Better? Good. But my f of x stays the same. All right. Let's see here. The rest of those examples are just working with the lines, right? And so, and I actually, yes? Oh, mm-hmm. In this case, because you're given x is, when x is 0, y is 2, that is your y-intercept, right? If you didn't have x is 0 in your table of values, then you would have to use the point slope form, right? Do you remember the point slope form of a line? So if we didn't have x we would need to use the point slope form of a line. And just to reiterate what that is, right, the line with slope m that passes through the point, so this can be any point, right, not necessarily the y-intercept, through the point x naught, y naught, sometimes, right, or x1, y1. But do you see what happens when I do my subscript ones? They look like commas and it gets confusing. So that's why I use subscript zeros instead, x naught, y naught. But it's just any point x, y, right? You could use a, b, or whatever you want. Then the slope, or the point slope form of a line says that y minus y naught is m times x minus x naught. And this is where we looked at the example of, okay, well, what if the point that I know is the y-intercept, right? In this case, 0, 2. Then my y naught would be 2 and my x naught would be 0, right? And then I would be able to rearrange this thing. So in this case, let's pretend that we didn't have the 0, 2 value. Let's say, but we do have the 2, -4 point, right? Let's say that that's a point that we know on here, right? So in our example, we know the point 2, -4 is on the line because it's in the table of values. Is on the line because it is in the table of values. The slope we still found was -3, so that's going to stay the slope. So now what we can do is we can say y minus -4, because that's the y value that I know, is going to be -3 times x minus 2, because that's the x value that I know. Just make a note here, that goes there, and this one over here. You can rearrange this to be y plus 4 is -3x plus 6. Moving that 4 over to the right-hand side, now we get y is -3x plus 2, which is hopefully what we landed on, and it is. Right. So even if you weren't given the y-intercept in the table, right, you can still use the point slope form of a line for any point. As long as you know one point and the slope, point slope, then you can find the equation of the line. Yeah. And especially for later on, I am assuming that you're going to go into calculus, right? So this equation for the line is going to be way more useful, right, than the y equals mx plus b, because mx plus b, it assumes that you know the y-intercept, which isn't always the case, right? Whereas this one, you'll always be able to do as long as you have a point on there and the slope, right? Cool.
This is kind of a weird question, but since you know that x has to be 0, you just plot 0 in there and then you just get y equals 2.
Yes.
It makes more sense to just put it into the y equals mx.
But so is what you're saying, one of the points that we knew was 0, 2?
Well, you know that
Right.
for the y-intercept, the x point has to be 0. So instead of doing -3 times x times 2, it's just -3 times 0 minus 2, and then you just get y equals 2.
But this x has to stay x. So if we're putting in a 0, it would have to go here, right? But if we think about if we have the point 0, 2, right? This is the y-intercept. Then you have y minus 2 is -3 times x minus 0, right? So then you have y equals -3x plus 2. So we have to leave that x, so the x and the y without the subscripts, they have to stay just x and y, right? Because we need it in the form of a line. So. The rest of those examples here, I'll leave for you guys to work on your own, because usually it's not something that I'll ask, but I wanted to put it on there. And so here, if you're given just the line graphically, you can find the slope, but that's not really how I want you to do it, right? Usually I give you a table of values, it's at the very least, or usually I'll just give you the function, right? And I ask you, what's the slope, what's the intercept, plot the line, right? Kind of moving forwards, not moving from the line to an equation, right? But it's there for practice, but this one's less important. Same thing with these other ones on the side. I wonder if I can steal them all. Right. These are just for extra practice. There are two word problems here, the landfill problem and the copper mining problem. But just remember, it gives you the linear function. And then, so you can sketch a graph, right? Because you can draw a straight line. You can find what's the slope, what's the rate of change, right? So it's the same problem, it's just got a couple of words around it. Right? But you're able to handle those. No. I expect you to know how to graph a line, right? Find the slope, find the rate of change, they're the same, right? And so, but besides that. Okay. All right. If you have a look at section 2.6, 2.6 is on transformations of functions. So let me just start a new page here. 2.6 is on transformations of functions. This is graphing functions, right? And so one nice thing is that this section, I searched high and low on the final exam. It is not on the final, right? This section. We will be transforming sine and cosine, right? So trig functions, but we'll get to those and then we'll spend more time on it, right? For these, just all the other functions, right? Straight lines, how do we transform them? Parabolas, things like that. Right. We'll just talk about briefly, but this is not on the final, but we will see it briefly on test 1. But it will be tested on test number 1. But after that, we can forget about it. Okay. The notes for 2.6 are quite long because it's got a lot of those blurbs just telling us what to do, all the rules, right? And so if we start having a look at these, right? But then the problems that we are expecting you to do aren't that bad. And a lot of these are optional at the end where you're actually graphing things and moving things around. And so kind of 29 to 52 and then 19 to 24, they're all optional at the end there. So if you've done, well, probably, this might be the reason everyone hates graphing, is because we can, graphing a straight function, like a straight line or a parabola or a square root or something like that, that's not so bad, right? It's when we have these shifts, right? So if we have to move them up, move them over, squish them, stretch them, because we can squish them and stretch them in the vertical direction or in the horizontal direction. And what I find is that the way it's done, or the way that it happens in the graph, is kind of opposite to what you think it's going to do, right? And so we'll start with the ones that kind of make more sense, and then we'll talk more about the ones that, to me at least, don't make as much sense. So if we have some C we're assuming that C is positive, so we can talk about it just kind of normally. Then if we have a graph of y equals f of x, and we add C, well, all it does is it shifts the f of x up by C units, right? So the whole thing, whatever the shape of it is, moves up 2 units, for example. If you have f of x minus C, it moves it down. So far, so good. Things are behaving the way you would probably expect them to. Okay. And there's little examples along the way in there, so. Same thing for horizontal shifts, except, let's see here. Here's where I get confused, right? Or at least I used to. Now I've managed to wrap my head around it. But so C is greater than 0, right? So C is some positive number. And then if we have f of x minus C, usually I would say, okay, well, I want x minus C. So in my mind, I would move to the left. But that's not the case. It moves it to the right C units. Yeah? And so what we have is if the curve is here, then we have f of x minus C. It moves it to the right C units. So for those ones, I mean, you can try a couple of things, right? But just remember, at least for me, I had to remember that it does the opposite of what I think it's going to do, right? And so if I have x plus C, that's when it shifts it to the left. Right?
You can draw anywhere at the left side or at the right side.
Well, here we're just illustrating, so here C is just some point, or some distance rather, right? So we've just shifted it from here to here. Right. Is that what your question was?
Yeah.
Sort of. So then, and then from here, right, we don't know what this function is, and it actually doesn't matter because it's always going to behave the same. If we do f of x plus C, it shifts it over to the left. So here, right, just to highlight that for me, if it makes sense to you, then that's good. But I don't think that I'm alone in thinking that that's backwards, right?
Yeah, y is the actual. So if like C is 4 and then like f of
Mm-hmm. So if you think, yeah, so if you think about this point, for example, oh, actually it's going to be 0 either way. So how about this point, right? It is kind of hard to explain, actually. So you've got your original x, and then to get it to the same point, you're gonna, if you take away 2, to get it back to that same point, right? Has to do with like the shift. So from here, which one's the original? From here, this is the original. And then, so this is where we want to get back to, right? And so if you think of, okay, well, if I want to get back here, then from here, I would have to do minus C.
Okay.
Yeah.
So
Yeah, that's how I had to end up thinking about it is, okay, well, if I want to get back to the original position, then I would have to subtract C, right? So subtracting C actually pushes me this way because then to get back, to undo it, I would have to go back
here. Right, because that's y.
Mm-hmm.
Because I guess the rule is y equals y, and then the red one is y equals y minus the shift forward.
Yeah, well, the y at x minus
the
shift. which happens to be more. I know. Like I said, this is the reason everyone hates graphing, right? But if you're ever not sure about this kind of stuff, just use Desmos, right? Plot the original one, plot the next one, right? And see what happens, right? You can always use Desmos, well, not in a test, but you won't need to use Desmos in a test, right? If you flip through a lot of these problems that I've given you, right, from 4 kind of onwards, well, maybe not 7, 18, but all on the 3rd page there, you're given an original function, and then you just have to match it to the equation. So, but let's have a look at some more of these. Oops. So what we've got here, right, you can combine these vertical and horizontal shifts. So if we have y equals root x here, right, and then if I do y equals root x minus 3, right, so x minus 3 means I have to shift all of these guys over by 3 in the positive direction, and then I'm moving up by 4, for example, right? I can do a combination of these. But the one thing to remember is that you're going to manipulate the x and then move outwards, right? And so you're always going to start at the very basic x and then move outwards. And so you would do this shift first and then move it up to 4. And if you had to sketch a graph, what you do is you boil it down to the most basic version of the graph, root x in this case, right? And then you do these transformations slowly, right? Starting at the x minus 3, right? Take some values of x, so add 3, right? Plot them again, then move them up. So we can do these together, but again, it's more something that I would expect you to be able to use Desmos for. It's not something that we have to really work at. We will work on it for the sine and cosine functions, making those shifts, because that's more useful. We can reflect graphs, of course. If you have a negative f of x, what that does is it just flips it on the x-axis, right? So if you've got an x squared, and then now you want to plot negative x squared, well, then it just flops down like this, right? So it just reflects in the x-axis. Whereas if you want to make your x negative, right? So y equals f of negative x, then you reflect it in the y-axis, right? Because now all your negative x's yield positive numbers, and all your positive x's, right, yield negative x inputs, is what I should say. And so just remember, if the whole function is being negated, right, then it flips on the x-axis, and if just the x is being negated, then it flips on the y-axis. Right? And there's nothing that I could write that would summarize it better than that, so I'm just gonna leave it there. Let's do a couple of these. I'll leave the fill in the blanks, but I want to do 4 here. So here, if we're looking at these guys, we've got our original function, f, and like I said, it doesn't actually matter what the function is so much as recognizing what's happened to it. Here, it looks like f was shifted to the right by 2 units, right? And so, well, I know that that's the same exactly. So I can write, okay, well, this is three. I'll write them there. Moving on to this one, right? I've shifted left 1 unit. No, said 1, but I meant 3. 1, 2, 3. Here I've shifted over to the left 3. I've got f of x plus 3. So I'm going to call this little guy graph 1. This one, I've moved up 1, 2, probably A, right? Because the moving up and down behaves the way that we think it's going to. It's the left and right that behaves, well, at least in my mind, opposite to how I want it to, right? And so here I've moved up 2, here I've moved down 1, 2, 3, 4, and so I've got up 2 is graph 2, and down 4. I guess I could clean up this one here. So if you're okay to recognize those, then I'm happy. Okay. Now it's going to get a little bit trickier with the vertical stretching and shrinking. And so vertical, remember, is this way, right? And so if you're stretching it or if you're shrinking it, right, then it's going to bulb out this way, right, or thin out this way. And so vertical is up and down. And it sounds like I had trouble with a lot of things, but I used to have trouble with like which one's the horizontal and which one's the vertical. But then I just think about the horizon is like this. So that's horizontal, and then vertical is the other one, right? So yeah, maybe I should stop telling you guys everything I had trouble remembering. I had trouble. Exactly. Oh yeah. Yeah, you can get a math degree, no problem. No, but I think it's good to know that it's kind of normal to not get this stuff right away. Yeah, right? Because I did feel like, oh man, like everyone else knows this stuff, and no, that's okay. You just have to think of things that remind you of what it is, and sometimes just knowing what you're not good at, that's all you need, right? And then you can kind of tackle it. Anyways, here we go. Here, we're multiplying f of x by some c, right? And so if c is greater than 1, right, so bigger than 1, right, so we're multiplying by this bigger number, then we stretch the graph vertically by a factor of c. And so what that's going to look like, right, is if f of x is this blue function here, then stretching it vertically, right, stretches it this way. And so now we've got this stretch, and so it's being kind of pulled up in this direction. If c is between 0 and 1, then you shrink it by a factor of c. Right? So if we were stretching it before when c is bigger than 1, then now we're shrinking it. And so here, this blue one is our original function. And so now we're shrinking it. And so now it's going to get smaller, right? Or the y values will get smaller. Okay. I'll steal the quick example because sometimes it's easier if you can just have a look at a couple side by side. So for example, if we're talking about f of x equals x squared, that's going to be this purple one, so the middle one. That's the one that we know the shape of. So this purple one, that's our usual parabola. And then here, if we multiply it by 3x, so now we have 3 times f of x, so 3x squared, then what happens is it's getting stretched, right? And so it gets thinner, and it's increasing faster. Whereas if you've got something between 0 and 1, right, 1 over 3 as your multiplier, then it's being shrunk, right? And so now it's being flattened out, and it's not increasing as fast. Okay. Let's see what else we've got here. I'll do this one next here. Then we can talk about the example. Because I did throw an example in there because I thought it was pretty useful. So we talked about vertical stretching and shrinking, and we can also have horizontal stretching and shrinking. And the horizontal stretching and shrinking is if we're manipulating x by multiplying it by c, whereas on the vertical, the c was on the outside of the function, and now on the horizontal, the c is on the inside on the x. Okay. And so again, if you've got c greater than 1, then you're going to shrink it graphically, or shrink it horizontally, sorry, shrink the graph by a factor of 1 over c. So here's our original function f of x, the blue one, and now it's been shrunk by a factor of 1 over c. Same thing if c is between 0 and 1. If c is between 0 and 1, let's pick a number that's in between there, 1/2, right? Then stretching it horizontally by a factor of 1 over c, well, 1 over 1/2, 1 over 1 over 1/2 puts me at 2 over 1, right? And so that's why it's getting bigger. I'll throw that example in here. If c is 1/2, right, then 1 over c is 1 over 1/2, which is 1 over 1 times, 2 over 1, which is 2. And so it's stretching by a factor of 2. Now let's steal this guy here. You've got it in front of you, but I do not. And I'll also steal the note that I kept in there because it is important. So like I said, if you have to graph something nasty like this, if f of x Hey, it's underlined properly. If f of x is 1 minus 2 times x minus 3 squared, what you're going to do is you're going to start with x squared, right? You're just going to take away all the extras and boil it down to just f of x is x squared. You know what the graph of f of x equals x squared looks like. It's this parabola, right? And so that's where this came from here. And then through multiple steps, you're going to manipulate this function and slowly build out until you have the function that you want. And so you're starting with the x on the inside. And so the first thing that you're going to do is you're going to shift it to the right by 3 units, right? Because you want to manipulate the x, and on the inside here, you've got x minus 3. So then the first thing you're going to do is you're going to shift it to the right by 3 units. So now you have y equals x minus 3 squared. Okay. Then we're going to, well, we've got a negative 2, right? The negative just says flip it on the x-axis, right? And so now I'm going to reflect it this way. There. But also I'm going to stretch it by a factor of 2, right? And so now it's stretched a little bit this way, so these things would have come out here, and now they're being stretched out this way. And then we're going to move up 1 to get the last transformation. So here, this is number 1, this is number 2, this is number 3, and this is number 4. And so to graph, let's call them a complicated function, right? So something that looks kind of nasty like that. F of x is 1 minus 2 times x minus 3 squared. To graph a complicated function, step 1 is to graph the most basic version of the function. So for example, if we have to graph f of x equals, what was it? Thank you, 1 minus 2 times x minus 3 squared, right? Then start with f of x equals x squared. Or even if you've got f of x is the negative root of x plus 2 all minus 1, right? Start with f of x equals root x. So you just boil it down to the most simple version of x, or x squared, x cubed, x whatever. And then you start manipulating it to get to where you want. So then the second step is from the x, right? So from the very core of the x, start to manipulate it to get to the function that you want. So from x, using order of operations, right? Brackets, exponents, right? So first we deal inside the brackets, do whatever we need to do in there. Using order of operations, which is just BEDMAS, make the manipulations, or we manipulate it. We manipulate the basic graph until we have the graph that we need. Until we have the graph that we need. Oops. Let's have a look at this one. Oh, sure. I guess it was two things. So here, right, we don't care about what f is. F is just a function, and we want to describe how the graph of each function can be obtained from just that basic graph of f. And so if we start, those first few that I gave you were a little bit too easy, so I'll give you the last few. Not too easy, but reasonable to do on your own. If we look at 18, A and B, right, or maybe we should look at, oh, how about we do 16 and 18? Let's start with 16. So 16A is 1 over 3 f of x minus 2 plus 5. Not really caring about what f of x is, right? The first thing you would have to do is shift this thing over to the right by 2 units, right? Because you've got the x minus 2. And so the first thing you're going to do is 1, shift right 2 units. Order of operations says that now I need to go, okay, so I've done what's inside the brackets. Now dealing with the x, right, I'm multiplying by 1 over 3. And so this is my second step. Glancing back right now, I'm multiplying my f of x, which means that it's going to happen vertically, right? And my c is between 0 and 1. And so then it's going to shrink it vertically by a factor of c, which is just 1 over 3, right? And so what we'll just say is we have to shrink f of x vertically by 1 over 3. And I'm running out of colors here. Last but not least, I have to move this whole thing up 5 units, right? So then shift the graph vertically by 5 units. I'll put in brackets up, all right, because it's positive 5. Let's do 18A. I'll leave 16B for you guys to do because it's very similar, but 18 A, let's do y equals f of 2x minus 1. Now x is being multiplied by 2, which from our notes, right, we know is a horizontal stretch or shrinking. C is greater than 1, which means we have to shrink it by a factor of 1 over C, right? So the C in this case is 2. And so our first step, and I'll move this down the same page. Our first step is to shrink, oops. Shrink the graph I keep messing up everything here. Horizontally by a factor of 1 over C. C is 2 in this case, 1/2. So shrink it down half. After shrinking it, then we can move it down 1 unit. Shift down 1 unit. Let's see. 18B we can do as well. 18B is, where is it here? Y equals 2 times, oopsies, f of 1/2 x. Always starting at our x and moving outwards, right? Now we're multiplying our x, and so that's a horizontal shrink or stretch. It's horizontal at least. And it's between 0 and 1. So it behaves a little bit differently, right? Because this is the one that we looked at, actually. And so we want to stretch the graph horizontally by a factor of 1 over 1/2, which is just 2, right? And we showed that earlier, 1 over 1/2, 1 over 1 over 1/2, 1 over 1 times 2 over 1 makes 2. Then my step 2, now I'm working on the vertical, and C greater than 2, which this case it's 2, so, or it's greater than 1. Oh my goodness, can't talk anymore. C is 2, so it's greater than 1, which means I have to stretch the graph vertically by a factor of 2. Stretch the graph vertically by a factor of 2. Oh. Any questions about those before we talk about the last concept here? So the last concept that we have to deal with is the idea of even and odd functions. And basically, if the power of x is even, you have an even function. And if the power of x, the highest power of x, is odd, you have an odd function. And so I will summarize that here. If the highest power of x is even, we have an even function. Oops. And vice versa. Similarly, if the highest power of x is odd, we have an odd function. Here, it summarizes that, okay, well, if you have an even function, it's symmetric around the y-axis, right? If you have an odd function, it's symmetric around the origin. Right? And so here, symmetric around the y-axis, I can kind of wrap my head around, right? Symmetric around the origin says that, okay, well, here, if I'm just working, swiveling around the origin, then we have an odd function. We can show mathematically if it's even or odd, right? Because if we take f of negative x and then we just get f of x in return, then we have an even function. If we do f of negative x and then we get the negative version of f of x, then we have an odd function. Right? We're not going to use it that way, but it's definitely something that you can do, right? And something that I've done in the past, made people do in the past, but it's not something that we'll work on. Let's flip to some of these questions here. So 25 through 28 is just matching the graph, and the absolute value of x is just two straight lines meeting in the origin, right? One negative slope, one positive slope, but otherwise they're the same. And so let's focus on this other one because I find it more interesting. If we have a look at 70, they look very similar, right? 69 and 70 are basically the same. So let's have a look at 70 here. So this blue one, which you can't tell it's blue in your printout, but here it's labeled f of x. And so here's our original function. And let's see if we can find one that looks the same, right? Maybe it's just been shifted. So sometimes those are the easiest to find, right? And so here, if I move this guy over here, then I've moved, right? That's the same graph. And so I've moved up 1, 2, 3, and then over 1, 2, 3, 4. And so I've moved to the right by 4 and up 3. And so this is graph number 1 for C. Graph number 1 is y equals f of x minus 4 plus 3. If we have a look at graph number 4, that looks like it's just been it's symmetric around the y-axis, which we just talked about. So, or it's reflected about the y-axis. And so, what did we say? Then f of negative x equals f of x. So I think we label these. If I had to pick one of these, then d, y equals f of negative x, is number 4. Okay. How about graph number 2? Graph number 2 looks like it's been shrunk, right? And so the only ones that's been, or the only one that's been shrunk on here is A, right? And it doesn't actually matter if it's on the X or on the, or if it's horizontal or vertical stretching, right? Because there are no X's that are being multiplied except by -1. And so the only option here is y equals 1 over 3 f of x. But you can convince yourself that, and I always get these mixed up, if I'm multiplying my f of x, it's the vertical, which makes sense because it's been smushed this way. So my graph number 2 is y equals 1 over 3 times f of x. By elimination, but also just kind of looking at it, right? F of x has now been flipped, which means I had to take the negative of it. And so negative f of x plus 4. So I had to shift over by 4, and then I took the negative of it. So y equals negative f of x plus 4. So this is what I would expect you to be able to do, right? Look at graphs, figure out which of these possible functions go with it, right? And there's a lot more that you can work on, but they're all kind of the same, right? More or less. Any of those that you want to do? Oh, well, 71 to 74, I guess, could be labeled optional, right? Because it gives you the basic function, and then you're supposed to do the transformation. But if you focus on 25 through 28, and then 69 and 70, those will be good. Any questions? No? All right. It's transformations. It's on test 1, but not on the final. No questions? See you guys on Friday. We'll finish chapter 2.